Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we will going to discuss about generation and detection methods of QPSK signals. So these are the outlines. We'll start up with the introduction, where we will discuss whatever we have studied in our last lecture about the introduction to QPSK system. Then we will going to discuss the block diagram description of QPSK modulator, which will be followed by the timing diagram of QPSK waveform. How does a QPSK signal waveform forms? Then we will going to discuss how we will going to demodulate or detect our QPSK signal, obviously with the help of block diagram. Then we will going to discuss various advantages as well as disadvantages associated with the QPSK system. And finally, we will going to conclude via discussing some of the applications of QPSK modulation. So QPSK is a bandwidth conserving scheme, which is the example of quadrature carrier multiplexing. In our last lecture, we have already discussed that it is analogous to our quadrature carrier multiplexing, provided the major difference between that is in quadrature carrier multiplexing, we are using two analog input message signals such as your M1T and M2T, and here in this QPSK, we are basically using digital bits, since QPSK is a digital modulation scheme. So it allows the signal to carry the twice as much information as ordinary PSK using the same bandwidth. So instead of passing single bit, we are actually trying to pass a group of bits, or we could say the combination of two bits at a time. That is why we can say that it can carry the twice as much information than the ordinary PSK signal. So although PSK can be viewed as a quaternary modulation, what do you mean by that? We could say that a single carrier which can have four different phases according to the group of bits, or we could say that according to the four symbols. So since it can have four distinct phase angles such as your pi by 4, 3 pi by 4, 5 pi by 4 and 7 pi by 4, that is why we can call them as a quaternary modulation scheme. But it can also be seen as two independently modulated quadrature carriers where the two carrier signals are 90-degree phase apart. That is what we mean by quadrature carriers. So in our last lecture, we had already seen the general expression for QPSK waveform, and it has been given as Sn of t is equal to under root of 2 Es by Ts cos of 2 pi fct cos of phi t minus sine 2 pi fct sine of phi t. So where phi t is the phase angle whose value can be your pi by 4, 3 pi by 4, 5 pi by 4 or 7 pi by 4 depending upon which group of bits have been selected, and Es signifying the symbol energy and Ts is the symbol duration. So this is we had already seen in our last lecture. So the above expression can also be written as Sn of t will be equal to Si of t cos of 2 pi fct minus Sq of t sine of 2 pi fct. The multiplier of cos of 2 pi fct would have been called as your in phase component, and the multiplier of your sine of 2 pi fct is called as your quadrature phase component of the modulated wave. From the last discussion, we can say that we can write our QPSK waveform in terms of in phase component and quadrature component. Likewise, Si of t times of cos of 2 pi fct minus Sqt times of sine of 2 pi fct. So where Sit will be equal to under root of Es times of under root of 2 by Ts cos phi t, and Sqt will be given by under root of Es times of under root of 2 by Ts sine of phi t. So this will be the value of your SIT and SQT respectively. So if we closely observe that this is the expression of our QPSK waveform, so we have to generate this signal in order to get the QPSK waveform. So this particular figure is showing the QPSK transmitter. So initially as an input we will be having a binary data sequences which will get passed through the polar NRZ encoder. What actually our polar NRZ encoder will going to do is it will going to generate a polar stream in regards with our binary data sequences. So what do we mean by that is, suppose our binary data sequences is 0, 1, 0, 0, 1. So what our polar NRZ encoder will going to do is, instead of 0 bit, it is producing some negative voltage, and for 1 it is producing some positive voltage, and then again for 0 it is providing some negative voltage, then again negative voltage, and then some positive voltage. So here lies the DC level. So then this polar NRZ encoder output will get passed through the demultiplexer's input. Then what our demultiplexer will going to do is, it will going to split our bit stream into two parts, that is in your A1T and your A2T. In some books, this particular blocks of demultiplexer would have been represented as bit splitter, which will going to split your bits into even and odd parts. So here what our demultiplexer will going to do is, it will going to pass all the even number of bits, such as this 1 and this 0 and the next bit, that will going to pass through this above product multiplier, and the odd number of bits, that is your 1, 3rd and 5th, these number of bits will get passed through the lower product multiplier. So the second input to the above product multiplier is the basis function, that is given by under root of 2 by Ts cos of 2 pi FCT. We had already discussed what do we mean by orthonormal basis functions. In our last lecture, we have described that why we are calling them orthonormal basis functions. The two special point about our orthonormal basis functions are, they are 90-degree phase apart and they are unit energy signals. So obviously this is a modulator, or we could say that our product multiplier. So our even bit, or we could say that A1T, will get modulated with this basis function phi 1T, or we could say that with this carrier signal under root of 2 by Ts cos of 2 pi FCT, and our odd number of bits, or we could say that A2T signal, will get modulated with this particular carrier signal whose value is under root of 2 by Ts sine of 2 pi FCT. So then the output of these two product multipliers will get passed through the summer, and the output of this particular summer will be your QPSK signal ST. Please keep in mind that the modulated signal where the carrier frequency is your cos of 2 pi FCT, we are calling them as a in phase component, and the product multiplier output whose carrier frequency is the sine 2 pi FCT, we are calling them as a quadrature component. So this is the description, whatever we have studied so far. So the incoming binary data sequence is first transformed into polar form by a non-return to 0 level encoder. We had already discussed that. Thus the symbol of 1 and 0 are represented by plus ES and minus ES respectively. So where ES is representing the symbol energy. So this binary wave is next divided by the means of demultiplexer into two separate binary waves consisting of the odd and the even number of input bits. This is what we have tried to explain in the block diagram structure. So then what we are going to do, that these two binary waves are denoted by our A1T and A2T. That is, we are talking about our even bits and odd bits. Here one thing should be noted, that in any signaling interval, the amplitude of A1T and A2T equals to SN1 and SN2 respectively. What are these SN1 and SN2? This is the amplitude of first bit in the nth symbol, and this SN2 is basically representing the second bit of nth symbol of QPSK signal. So depending upon the particular debit that is being transmitted. So obviously the combination of these two bits would have been called as your debit. So we had already seen that there are four possible symbols, that is your 00, 01, 10 and 11. So these are four possible symbols in our QPSK signal. So the combination of these two bits is called as your debit. In general, the combination of these two bits, we are signifying them as a symbol. So the two binary waves, that is your A1T and A2T, are used to modulate the pair of quadrature carrier or orthonormal basis functions. So obviously the inputs to the two product multipliers are A1T and our first orthonormal basis function phi 1T, that is your under root of 2 by Ts cos of 2 pi FCT, and the input to the second product multiplier is your A2T. With the second input as a carrier, we have under root of 2 by Ts sine of 2 pi FCT. So both the carriers are orthonormal basis functions, which would have been given as phi 1t is equal to under root of 2 by ts cos of 2 pi fct. This is what I had already said. And your second orthonormal basis function is under root of 2 by ts sine of 2 pi fct. These are our two quadrature carriers. So the result is pair of two binary PSK signals which can be detected independently due to the orthogonality of phi 1t and phi 2t. So obviously we could consider them as the two binary PSK signals where the first component have the carrier signal as phi 1t and second component has the carrier signal as phi 2t. So although both the PSK signals will going to possess the same frequency, but still they are not garbled or they are not interfering to each other just because they are orthogonal to each other, and hence they can be detected independently. So at last the two binary PSK signals are added to produce the desired QPSK signal, and that signal we are referring as ST. So this particular figure is showing the timing diagram of QPSK waveform. So how QPSK waveform will going to look like. So in this particular figure, this above portion is actually showing the in phase component, and this second wave is actually showing the quadrature component. So in the in phase component, we are modulating our signal with the help of cosinusoidal waveform, whereas in the quadrature waveform, we are modulating our signal with the sinusoidal waveform. So these numbers 1001, 1010, these are basically representing the bits which will get modulated with the help of in phase and quadrature carrier signal. So you can also call them as your A1, and this group of bits or combination of bits you can call them as your A2. So this I and Q signals are basically representing two PSK waveforms. So in summer, when we are going to combine these two in phase and quadrature signal, we will going to get this sort of waveform, which is nothing but your QPSK signal. Here the value of phase angle should be properly visualized, that in the in phase channel component the first bit is 1 and the carrier signal we are utilizing is cos of 2 pi fct. So here that is why this particular signal will going to start with this cosinusoidal waveform, whereas this particular signal is starting from 0 as this is your sine signal. So as the bit value changes from 1 to 0, there exists a 180-degree phase shift. You can see it here, this is your plus 90 and this is your minus 90. So the overall phase difference turns out to be your 180-degree. Here again in the same phase, since bit is same, so there will be no phase change. Then again when bit changes from 0 to 1, there again exists a 180-degree phase shift. In the similar manner, we can also see in our quadrature channel component too. So initially its value is sinusoidal signal like this one, and when the bit value changes from 1 to 0, there exists a 180-degree phase shift at here, and here also when the bit changes from 0 to 1, then there exists a 180-degree phase shift, and similarly when the bit changes from 1 to 0, there also exists a 180-degree phase shift. So one should keep in mind that QPSK signal is the combination of these two signals. So we will going to add up these two components, that is your in phase component and quadrature component, in order to get our QPSK signal. Here we can say that the phase is actually changing at the symbol changing interval, such as here we will be having a symbol 1 1, and in the next cycle, or we could say that in the next symbol period, when this symbol value changes from 1 1 to 0 0, there exists a phase shift, and when again this symbol 0 0 will get changed to 0 1, there also exists a phase shift, and similarly at this particular interval also, when the symbol changes from 0 1 to 1 0, there exists a phase shift of 90-degree from the previous one. So this particular signal is actually showing our QPSK signal. So now how we are going to demodulate our QPSK signal. So this particular slide is showing the coherent QPSK receiver structure. So at the input side, we will be having a received signal ST, which will get passed to the bank of two correlators, in which correlators one's second input is your carrier signal, which is denoted by your phi 1t, that will be equal to under root of 2 by ts cos of 2 pi fct. which is nothing but your basis function, or we could say that in phase basis function, whereas in the second correlator the carrier frequency input is denoted as phi 2t, which will be equal to under root of 2 by ts sine of 2 pi fct. Here one should keep in mind that both these correlators will going to get the same input st. Then this correlator signals will going to pass through the integrator. So let us say this integrator 1 output is your x1 and this integrator 2 output is your x2. Then this signal x1 and x2 will get passed through the decision device, which will going to compare the strength of x1 with the threshold 0. If the value of x1 is greater than 0, then it will going to take decision in favor of 1 bit, and if the value of x1 is less than 0, then it will going to take the decision in favor of 0. And similarly, in this second decision device, the value of x2 will get compared with this 0. If the strength of x2 is greater than 0, then decision will be going to made in favor of 1, and if the value of x2 is less than 0, then decision will going to take in favor of 0 bit. Then after that, these two bits will get combined with the help of multiplexer, and the output of the multiplexer will be the desired bit stream as we have generated at the transmitting side. So this is how we will going to demodulate or detect our QPSK signal. So now this particular slide is showing the brief description whatever we have discussed so far in our last slide. So the QPSK receiver consists of a pair of correlators with the common input and supplied with the locally generated pair of coherent reference signals, that is your phi 1t and phi 2t. This is what we had already discussed, that your QPSK demodulator is containing two correlators in which we will going to pass same common input, and the second input for correlator 1 it is your phi 1t, and for correlator 2 it is your phi 2t, whose value would have been given as under root of 2 by ts cos of 2 pi fct and under root of 2 by ts sine of 2 pi fct respectively. So the correlator outputs x1 and x2 produced in response to the received signal st are each compared with the threshold of 0. This is also we had discussed that the correlator's output signal is designated as x1 and x2, and they will get compared with the 0 threshold. So if the value of x1 is greater than 0, then decision is made in favor of symbol 1, or we could say that bit 1 was transmitted for in phase channel output. But if x1 is less than 0, a decision is made in the favor of symbol 0, or we could say that bit 0. Here you should not confuse with this symbol 0 and symbol 1. They are basically signifying 1 bit and 0 bit, and in generalized format or the combination of 2 bits we are calling them as a symbol in QPSK. So please don't get confused. Here this symbol is representing bit 1 and this symbol 0 is representing bit 0. If the value of x2 is greater than 0, the decision is made in favor of symbol 1. This is the same thing as we have done earlier, or we could say that this is the same decision outcome that we have taken for in phase channel. So finally these two binary sequences at the in phase and the quadrature channel outputs are combined in the multiplexer to reproduce the original binary sequences. So this is how we are actually detecting the original bit sequence. So now we're going to discuss some of the advantages and disadvantages of QPSK. So some of the advantages are it has very good noise immunity. It means noise will not going to affect it into greater extent. Then the second advantage is baud rate is half of the bit rate, hence better utilization of available bandwidth. So hopefully you should know about the bit rate and baud rate. If not, then in short I can tell you that number of bits transmitted per second would have been called as your bit rate, whereas the number of symbols transmitting per unit time we will going to call them as a baud rate. So for the binary signal transmission, the bit rate and baud rate has no significance, both are same. But when we are talking about M-ary signaling schemes, bit rate will always be greater than the baud rate. So in this particular example, as we are using QPSK signal, we can say that the bit rate is 2 times than the baud rate. And the next advantage of QPSK is it is having low error probability. It means its transmission quality is much superior. That is, if we are using QPSK as our transmission modulation scheme, then throughput will be higher. The disadvantage of your QPSK is the generation and detection is quite complex, as we had already seen that it requires many components such as multiplexer, demultiplexers, as well as correlators, etc. So obviously the circuit is quite complex. So now the applications. So QPSK is being used for satellite transmissions of MPEG-2 video transmission. So this is basically your signal compression format. So it has been used for satellite transmission. Iridium satellite communication system. Iridium is a lower Earth orbit satellite communication system where we are using QPSK. So in cable modems also we are using QPSK. CDMA systems also exploiting QPSK signals, and some other forms of digital communication systems over the radio frequency carrier signals are also using QPSK. So these are the certain application areas where we are using QPSK signals. These are the references. Thank you very much for your patient hearing.